If you move your head to the left, it will.
You can do like this. Huh? Oh, this should be good, huh? All right. Like this. Oh, I guess.
All right, so good morning, everyone. I'm excited to be sharing the keynote presentation for today from Davide Balzarotti.
Perfect.
So David is a full professor and the head of the digital security department at Eurecom. He's been involved in the organization of major conferences in the area. Today he's here sharing our insights about malware. And I mean, more than other highlights, I would probably stress the following. So we got two very prestigious European Research Council grants, Consolidator and Proof of Concept grant. So these are, if you don't know, these are very prestigious grants provided to the best European researchers. So without further ado, I'll give the floor to your presentation. Thank you so much for coming.
Thank you very much. Okay, can you all hear me? Good? Okay, perfect. Thanks for the introduction. Good morning, everyone. My pleasure to be here. So today we're going to talk about malware research. When I accepted to give this keynote, I had three objectives in mind. So I wanted to try to distill this research, well, a lot of papers, like thousands and thousands of papers, and try to identify the main questions that we as a research community, we try to answer over the years. And then I had the objective to try to see whether we were able to answer these questions. And finally, to give you, my list of open problems, just to pick something to discuss about. So let's be honest. It was working 1 second ago. Oh, wait. There's a message here. It now works? Now it works. Okay, good. So let me be honest with you. I think I failed at this. I was a bit too ambitious. I spent 2 weeks rereading papers from the 90s. A lot of good stuff. I rediscovered stuff. I found new papers that I was not aware of it. And I finished my slides 2 days ago. And I think I had enough material for the entire conference to cover 3 days of conference. And then I spent yesterday locked in my hotel room, tried to cut and cut and cut and try to get down to 1 hour. So we'll see if I manage it. But, that was not so easy as I thought at the beginning when I had this plan in mind. All right, so let's get started. So we start from the beginning. So the beginning, some people say that this started before, but from a research point of view, for me, the beginning is the University of Southern California, beginning of the 80s. And in particular is the lab of Leonard Edelman, so very famous cryptographer. And so you will not maybe expect malware to start from the lab of a crypto person. But one of the students, Fred Cohen, wanted to experiment with self-replicating automata or self-replicating code. Didn't invent this. This actually dates back to the 40s, actually, von Neumann wrote something about it. And Fred Cohen also didn't invent viruses, technically. There were already some self-replicating code existing. DEF Cloner probably came out a year before or something like this. But he's the first guy to actually study this, from a research point of view. So I did this PhD on it, and good, theoretician. He started with a formal definition. You can find it here. We don't have time to discuss it, but it's actually also very interesting to look at this definition because it defined what a computer virus is from a formal way, but also not just the virus itself, a virus set. So he already had in mind this idea that when virus propagates, they change form. Okay? Very interesting stuff. But what we care the most is the fact that in his PhD thesis, he actually came out with the first research question about malware. There was, we all know about it, the problem of whether it's possible to write a program for a Turing machine that is able to tell whether a sequence is a virus or not. And, good boy, he was able actually to answer this question. So Cohen actually found an answer for this, and he said, no, we all know about these results. We all know that it's undecidable, actually. It's an undecidable problem, so we cannot write a generic virus detector that can find all viruses. So we started good. Don't get used to it, because most of the question we're not going to get an answer like this, but that's nice. So now I'm going to use this sort of metro map to try to give you an idea of what I'm talking about, right? So we start from theory, because that's where we come from. And we start from the first paper there, Fred Cohen, Theory and Experiment of Viruses. Interesting the fact that he wrote this paper as a single author without his advisor. even though the advisor was the one that actually gave the name to computer viruses. Then, also interesting, his advisor, a bit less known, this paper, wrote a follow-up the year after, this time without his PhD student. I don't know what's going on, I don't know, California in the early 80s, weird way. So they both wrote a paper, they worked together, but, both as single authors. This actually was published a crypto. I don't know how many crypto papers you can find about malware. That's probably the only one. But this is actually a very good piece of work, much less known. But what Adamant did is he expanded the definition of virus to include also things that are not self-replicating. So Trojans, for example, he called that EPIAN. That name didn't stick. I mean, virus was a good one, this probably not. But anyway, and then he went on doing some math to actually prove the complexity of the problem, not just the fact that it's undecidable, but actually complexity class. So very, very good paper, very broad, a lot of interesting research question at the end. But here we have these two first problems that we try to address. So one is how to formally define this malicious code, and then how to prove mathematically some properties of it. So the first line of research, interesting. Actually, in the conclusion of the paper, Adamant says that detecting viruses is intractable, and thus seems unlikely that protection system based on virus detection will ever be successful. That was the first year that the antivirus industry started, and that, it was a theoretician, so didn't get much, maybe the possible money you can make out. But anyway, we'll get back to this later. So the first line of research on top here continued for a few years. So it was very popular in Europe, for example, in France. A lot of people tried to refine this definition and try to expand it because you wanted to have actually a definition of malware, of malicious code that was a bit broad. So they add, for example, polymorphic viruses. Then they add, more broader formalisms. And this thing went on for, maybe 10 years or so, and eventually then died. So we sort of stopped doing this. But this was very influential, that's why I mentioned it, because a lot of people got inspiration from this, analogy with, normal viruses. For example, the very famous paper, Computer Immunology by Stephanie Forrest, that then started all the intrusion detection thing, came from this analogy and this idea. So very influential, but probably not, a lot of interesting results after the first couple of pages. On the bottom here, instead, if you look at the what we proved, then here for a few years, we went on proving more and more things. So at the moment, we know that it's undecidable the problem of writing a generic virus detector. Then here, just in white, they show that actually you can even write individual viruses, even if you know them, it's impossible to write a detector with 0 false positives. So problem gets worse if you want. It's not just the generic detector there. And then we have a paper from Somash, Song, etc., that shows that even the problem of finding a particular malicious behavior within a sample is undecidable. Wenki Lee then went on to show that even the problem of unpacking is undecidable. And okay, I spare you all of them. There are a few dozens, but we got the point. So everything that you try to ask about a computer virus or about malware, which in general is actually everything you try to ask about a computer program, is often undecidable. Okay? So not so maybe interesting at this point. But what I find more interesting is the fact that few people actually start thinking that, okay, the general problems, fine, we can solve them. But what if you put some constraints? And here I selected two papers that I think they're, very interesting. The first one is not very well known. It was a paper that was actually published in the IEEE Transactional Information Theory, another place where you don't find a lot of things about malware. But the author here, Spinelli, says that, okay, if we put some boundaries on the length of this, then it's not undecidable anymore. The problem becomes NP-complete. And he says even in the paper that you can write a good enough detector if you can tolerate few false positives that actually work in linear time. So that was the first thing I could find. In the meantime, of course, the antivirus industry was selling antiviruses like hell, so they had some solution. But from a research point of view, that was one of the first papers that says, you know what, maybe we should give up with the idea of solving the general problem and focusing on something a bit more specific. And the other paper is actually for Michael Bailey, not a theoretician, but again, in a paper went on to show that if you, this is about unpacking, it went on to show that if you put boundaries, in this case, either on the time or on the space that the unpacking routine has at its disposal, then the problem again becomes NP-complete. And in the paper, the authors say, you know what? Other disciplines, they cope with NP-complete problem all the time. You just write, an approximate algorithm or something like this. You don't need a perfect solution, maybe, and you can find solutions that work relatively fast, and they can be used in practice. So these two are the first two works that they try to hint in the direction of, okay, forget about the general problem. Let's stick to something that we can solve. The other line of research in the theory that I selected here is about epidemiology. Also interesting because you link back to this problem of tractability. So here the problem was, how do we mathematically explain how computer viruses and then later malware in general spread? So we started with, again, a lot of mathematical formula, and we, over a graph, and try to basically copy what we know about, real viruses and try to see how we can adapt them to computer viruses. But again, here, interesting in the first paper about that, Kefar and White. So these are actually people from IBM. IBM was on fire at the time. I mean, 90% of this paper in the 90s, they were about IBM. We missed them. Good, so this is a paper from IBM, and they describe the first thing. And in the paper, actually, they conclude that even though Cohen showed that a perfect defense against computer viruses is impossible, we show that actually this might be unnecessary. And why? Well, because in some cases, viruses will not spread because they are under the epidemic threshold. So the intuition here was that you don't need a perfect detector. If you can detect malware good enough to sort of remove it before it spreads worldwide, then you're good. Then you'll probably achieve your goal without a perfect detector. So if you put this thing together, we see where we're going in the fact of, okay, maybe we find this sort of solutions. But then we went back to mathematical stuff. We forget this for a moment, and we start refining this, idea of spreading. This is the first paper I found in which people start, again, IBM, in which people start discussing not only mathematical formulation for the spreading of viruses, but the idea that you can actually sort of use the prevalence of virus encounters based on real world data. So you estimate how likely it is to find things. And this is actually still a current research topic at the moment. Then we wait a few years and the big worms came out. So early 2000, year of the big worms, and everyone jumped on the, here on the problem and start writing, models for how this worm propagate. They were all inspired by real world data. Here I put one paper, but there are a few dozen. In which people try to model the spread of this worm because it was a big problem, how fast it can propagate, how many hosts it can reach in a certain amount of time, et cetera, et cetera. And then this line of research didn't die out, as I mentioned. It still exists today, but mostly people here focus on encounters, how to estimate malware encounters in the enterprise, end user, et cetera, et cetera. So there are several papers on this topic. It's still a research area, but quite niche. Okay, so this is all I have about theory. I'm not a theoretician, but I think these were the three main questions that people try to answer in the first 10, 15 years of research on malware. So what did we learn? So we learned that the analogy of these biological system viruses was very powerful at the beginning. It actually inspired a lot of papers. I save you the bad one. There are a lot of bad ones. So at a certain point, probably we should have stopped using this analogy. We went a bit too farther, and there are, several dozen of papers that are very weird in that topic. But it was a good analogy. Epidemiology evolved, and it's still a research area today. We now use real data, as I say, to try to estimate malware encounters. And then we find out that everything is undecidable in the general case. It becomes an NP-complete problem if we actually put constraints to it. And then we figure out that probably we don't need perfect solution, but just a good enough detector will do the job. That's my 3-second summary of 15 years of research. So now we move from theory to practice. Okay, so at the beginning, this was mostly a problem for people working in crypto and theoretical computer science, and then later on it became a system security topic. So here we start with the detection because that's the problem where we are trying to solve at the beginning. And here I selected 3 main problems. So detector existed already. The industry had detectors, malware detectors, and we all know that they work using signatures, typically by signatures, and using heuristics that they try to, tell whether something is probably malicious or suspicious. So the first research question we try to answer is, how do we generate signatures? How do we make them more robust? And whether can we write something that we can use to detect unknown malware for which we don't have signatures yet. So let's start. So signature generation. Still at the beginning of the 90s, we have the first paper here. Again, IBM. And what is interesting is that IBM wrote papers at the time explaining always what they did in production. So there was not this problem we have today that, academia goes one way and industry goes the other one. At the beginning was, industry even writing paper, and he was telling you, hey, this is actually what we use to write signatures for our antivirus. So interesting. From a research point of view, maybe not rocket science. I mean, yes, you can extract subsequence of bytes, then you test it over, goodware in order to try to find those that they generate false positive, and you try to reduce this to some signatures that will work in practice. Then we get to the era of the big worms on the internet. And here again, a lot of papers on how do you automatically write signatures for worm. This become more practical because humans didn't have time to write signatures for this worm. They were very fast. By the time you figure out that there is a new worm, it's over in 2 minutes. So you really need to automate a system that immediately collects something and writes signatures. Many papers on the topic. Here, probably the 2 best solutions sort of that they came out, Polygraph and AMSA. And the idea of Polygraph was that if you have this internet worm, even though they might be polymorphic, you always find little subsequence of bytes, maybe in different orders, that they need to remain constant for the worm to work. For example, the return address that you need for a buffer overflow. So this intuition allowed them to generate signatures in an automatic way, starting from these existing copies of the worm. And then, of course, academia went on and saying, no, you're wrong. There are 2 problems with that. First, since you learn the signatures, we can sort of pollute the data that you use to generate the signatures. This is still not machine learning, but became big later on. And then other papers, came out and they say, no, look, it's also wrong the fact that the assumption that there is always a fixed sequence. So you can actually write worms that they don't have any fixed sequence, so you cannot actually recognize it. We're very academic, like a better model, and I break it and so forth. So let's leave this research here for a second. Let's look at the other. So the other is the heuristics. So we know that antivirus companies use heuristics. So this is the first documentation I found in a paper. It's actually a virus bulletin in which this guy from industry shows that, okay, how do these heuristics work? And if you see there, that's the example in the paper. They say, well, you look for a program, for example, jumps at the end of its code. Then he looks for files on a disk. And if you find something with a certain extension, he opens it. And you can understand where we're going, right? So if you get something like this, most likely it's a computer virus. You don't need to have a signature for it. It's something new, but most likely this is a computer virus. Yeah, in this old paper, there are always weird stuff. Like this guy, actually, the paper is called like something like 2000, right? And this guy actually said, you know why I talk about 2000? Because now MS-DOS is, almost there. And we have Microsoft Windows. Microsoft Windows is much more secure than MS-DOS. And since it's much more secure, it's harder to write malware for Windows. So we're gonna have fewer malwares. And actually, also the other problem is that it's more secure, so viruses will not spread so easily. So guess what? Regrettably, there will be no such as a vast antivirus market, and most of today's antivirus experts will have to find another job. Unbelievable, yeah, not quite correct. So the first big paper I found on this topic actually is from Somesh, and it was about behavioral templates. This was a big paper in which they say, okay, we can generalize this idea of heuristics about malware and try to write a language to detect this sort of malicious behavior and try to find this malicious behavior by using static analysis inside the code. Starting from that, it was hard. So here there are maybe 100 papers coming up, and it's hard to summarize them all. So I asked ChatGPT to do that for me. And this is a very good picture of what happened in the next 10 years. So here we have all sorts of possible models we can think of, right? So all possible type of features. Okay, let's try to detect them based on, API calls, on n-grams, on, the control flow graph, anything. And then try to compose in any possible rule, way, or other formalities that you can think of. And everyone claimed this is great and this is very robust. And then there is another paper that says that's not robust at all. We even have cases of very good papers published at Oakland in which exactly the same author, 6 months after, they publish a paper to show that they can evade their own system. That's more or less when I started doing research on this area. It was very fun. It was very easy to break everything. But I think if you read one of these papers alone, you don't learn much, frankly. I mean, it's just, yeah, you can use this model and you can write signatures that way, probably. Good enough. So here we have a gigantic pile of papers. And I just want to mention a couple of one. So this is limit of static analysis. It's actually saying something that everyone knew already. But since there were 1,000 papers trying to do otherwise, we wrote down in a paper that, you know what, it doesn't matter how sophisticated is your approach. If you write models based on pure static analysis, then you can cope with obfuscation and packing. Yes, there are papers that say we can try to deobfuscate. Our is very robust against certain classes of obfuscation, but eventually you're going to lose this battle. So people say, okay, well, you got it, and they start using instead dynamic features. So API calls became very system calls became very popular. A lot of people start writing models based on system call, graph of system call, dependencies of system call, and whatnot. And again, there are a lot of papers here. Is hard to summarize. Here I mentioned one of mine in which we try to make sense of this research because there were a lot of models and try to all test them once against the other. But frankly, also, if you read my paper, probably you're not going to learn much. I mean, it's just sort of a very chaotic area. We don't have time to go into it, but here we have the sub-branch of botnet detection. Very interesting, lot of papers, because here is, again, it's a behavioral model only for the network traffic. So there are specific solutions, that we came out there, bot hunter and exposure and stuff like this, but not much time to go into it. Now I move to the third sort of question that we try to answer in this area. So as a research question, we start saying, okay, now how do we test all these techniques? How do we test antiviruses and all the techniques that we are developing? Well, first of all, the industry was doing that. And actually, there is a lot to learn from this that is being sort of lost. So at the time, industry was testing antiviruses by using a methodology that was saying, look, you need to test your antivirus on all the samples that are known to be spreading in the wild. This was called in the wild. And actually, to know which one they were in the wild, there was a list. It was called the wide list. Actually, it came out in '96, yeah, and it was published until maybe 2010. So every month there was this list updated with the samples that the industry found in the wild, and you need to detect them all. And then there was the zoo. The zoo is all this malware that antivirus company knew it existed, but it was not found in the wild. And that was the vast majority, actually. And so then you need to show also that you can detect some of this, but it's a different problem. So initially, the industry had this idea in mind that, well, you need to detect what is out there, and you need to be good at it, and then you need to detect what it could be out there, but it's not. We completely lost this distinction. Academia, forgot it. I think it was an interesting idea. So next, we have a paper, again, virus bulletin. So in which they documented how they test the heuristics, because that's a different thing. And not rocket science, but again, he explains that to test the heuristics, you want to take the heuristics of today, check it on malware that comes out 6 months after, and try to see how it works. Difficult to find this paper, but very interesting if you look. There are a lot of results. And it shows that actually for the antivirus software that existed, most of the time the heuristic worked extremely well. So they had, I don't know, 70% probability of detecting viruses from the future, which is way above what I would expect, with one limitation, which is, well, for PE32 files, that didn't work quite well. So basically for Windows malware, which is the one we care the most, didn't work. For macro and etc., that was good. But for binaries, that didn't work quite well. Academia, oh yeah, another interesting thing. This virus bulletin people. This guy was, in the conclusion, was very, worried about the fact that the signature database of this antivirus is getting big. Semantic database is 6 megabytes. And if we don't do something fast, it will become 10 megabytes. I don't know why in 2005 you care about 10 megabyte database, but that was one of the main things that we should really try to address. Anyhow, academia, again, Somesh, one of the first to work on this topic, he wrote testing malware detectors. So here was the first idea of the fact that when you want to test these detectors, you don't want to use only known viruses, or let's not talk about malware, known malware samples. But you also want to take this malware sample and you want to mutate them. So you want to generate variation, and then you want to use this one to test antivirus, to test the robustness. This became very popular later with machine learning, but it was a good thing, basically. You don't just test with the existing virus, you test with variation of this virus. It's still an open problem. So the idea of which sample do you need to use to test this technique? We still don't really have a solution for it. It's, any paper that publish guidelines will tell you, yeah, you need to pay attention. And there are some things that you need to do, but it's still sort of an open problem of what we need to actually select for testing antivirus techniques. And here we have the sub area that I only mentioned one case that, well, there are many papers here on, okay, if you want to make a data set to test malware, then you need AV label. You need a label for, ground truth for the samples. And that's a big research, well, not, but, it's a separate research area of how do we do that? We do it by agreement, how we keep track of these changes, et cetera, et cetera. So what did we learn from this part? So first is that we keep forgetting that detection model can be evaded, period. I mean, we've wrote way too many papers just to show that another model can be evaded. And that was obvious since the beginning. It was an approximate solution. Then we wrote any paper that you read on this area for like years, you start by saying real antivirus used by signatures, and by signatures are very bad. You do something else. Well, they're not very bad. They still exist today. They actually do most of the jobs here today. Then we try every possible model we can think of. And we always find good results. For years, every single paper said that was great. Then, okay, we agree that, yes, if you do it with static analysis, yeah, probably we have limitations. And maybe we should use something else there, runtime information. We find out that instruction level information are always the most powerful information. So if you can use that, yes, then you can get very good results. The problem is that collecting the instruction is very difficult to do statically because of obfuscation and packing. And it's very costly to do dynamic. You need emulation, and that costs a lot. So people use syscalls, but we see later that we have problems with that. And finally, we still don't know exactly what to do for the dataset problem. We forgot about this distinction of in the wild and the zoo, and maybe that's something we should still probably use, but that's still an open problem. All right, so we don't change problem. We don't change problem. We remain on detection, but I sort of separate this line. This is machine learning because it's just way too big. Interesting fact. So machine learning, a lot of people think that one of the first security used machine learning since a very long time. A lot of people say that intrusion detection was one of the first applications, probably because that was where a lot of submission came from at the beginning. But actually, if you look at it, malware research was probably one of the first adopters. The first paper about machine learning on malware is 1995. Guess what? By IBM. And they actually wrote a machine learning, a neural network to detect boot sector viruses. And again, it's cool because not only this was the first paper on machine learning for malware, this was actually used in production, which is absolutely crazy compared to all this paper on machine learning for IDS that they never work in practice. This actually was used. Okay, it was sort of a niche, boot sector viruses, but if you read a very simple model, but already interesting stuff. Same people, we need to wait 5 years. And then they start saying again, IBM, start saying, okay, you know what? Now we have machine learning also for detecting regular malware, like PE files. Is a bit different here, the neural network. But if you read the paper, again, quite interesting because it's already talking about interesting stuff for the future. So for example, they say, look, our neural network is kind of small, and because we don't have enough training data. So if you want to make it bigger, well, we'll need many variations of the virus to train the hidden layers. And at the time, there were not so many malware, so that was sort of one of the limitations they had. And also very interesting, if you read the conclusion, the papers say, results indicate that detectors generating these procedures they cannot be the only way to detect malware. This is only something we can use on top of signatures, basically to detect unknown stuff. But this is not there to replace signatures. And this, again, was IBM probably using this. And then we forgot about this. And, a lot of people say that, signatures are dead, and we use machine learning. The industry didn't have this in mind. So one of the first papers here from academia is a paper from South Solfo here. And here is one of the first papers in which we start proposing other set of features to use for machine learning, not only like sequence of bytes and grams, etc. We have strings, we have API codes, we have DLL imported, etc., etc. This is also one of the last paper that if you read the result, it seems like it works so and so. Right? Accuracy is good, false positive is very high, 4 to 6%. just have to wait a couple of years and we start getting the first paper with 0.996 and area under ROC curve, which seems like, okay, great, problem solved. And then we start the other messy area here. So here we got the machine learning community looking at the malware problem and say, ooh, juicy. You know, we've been working on ideas for a while. Let's now try to solve this problem. Couple of thousand papers written on this topic, trying any possible model you can think of, any possible set of features. We just forgot what we did before in static analysis. We just reinvented all. And again, it's very hard to summarize. I give you an example here. I like this picture. This is from a survey on Android malware, actually. These are papers only that they propose machine learning for Android malware detection. You see how many techniques and how many papers, and this is only for Android. It's absolutely huge, this sort of research area. But thanks God, you don't need to read them. Actually, most of the papers there follows this sort of recipe. Take a malware dataset, forget about semantics, meaning, anything. Just treat it as number or as graph or whatever you prefer. Feed it to an algorithm that was designed to solve a completely different problem. Then, if it doesn't work, remove some part of the data, like PEC data, PEC sample, etc. Then tune the parameters, and you get 99% accuracy, and you publish the paper. There are probably a few thousand papers of this. And again, I think if you come from another planet and you read one of these papers, the only thing you learn is that malware detection is solved. Done. Well, works. Great. And they all reach this conclusion. I was not a big fan of this sort of period, to be honest. But later also, I was skeptical about this machine learning thing. But then if you long enough that we exhaustively try everything that was possible, then we actually start writing good papers on this topic. Here, there are way too many good papers. I select 5 or 6 to give you an idea. So the first here that I like is this paper. Again, not maybe a top papers, but this is one of the first papers to talk about the fact that why all this guy gets so high accuracy all the time. And one of the things that they notice is that, yes, you use random sampling to do, training and testing. And by doing this, you use sample from the future, information that was not available yet, to detect this from the past. That's not good. And actually, they show that if you actually use information that is only available at that time, the accuracy goes down quite significantly. And then they also discussing the problem of concept drift. So the fact that data changes, and then your classifier doesn't work as well once you deploy it. So very interesting problem. We'll still discuss it later. The year after, we have this paper. This is DINVA. Actually, I was in the audience where they presented it. And I remember my question to the authors is, why did you submit this to DINVA? And to me, this was a straight Oakland paper. A very good paper, actually, from Google and some research in academia. But the point is, here they show that first, there is a problem also with label inconsistency. The fact that labels change all the times. And if you use those in the future, you get information, you're cheating, actually. But then what they did was very interesting is the fact that they show that if you have a classifier, then now we start realizing that, okay, they don't work so good as they all promise. But if you can put human in the loops to give very few, classification done by humans per day, very selected, then you can really boost the results by using few, experts in the loop. Very interesting, I think that should be probably explored more. Then we have the very famous paper from Peppernot, in which basically what they did is they say, well, we worked so much on image machine learning for image detection and pictures and stuff. And let's see malware now, right? And there are 2 things that were known. First is that you can generate adversarial samples. And then Peppernot went to show that if you generate adversarial samples, yeah, you will break most of the models that are out there. Not so surprised, actually. But then more interesting is that they took 2 mitigation for adversarial samples, distillation and adversarial training. And they showed that on malware, actually, distillation didn't work quite well, but adversarial training did. So if you use adversarial training, then the model becomes more robust. The little picture there, because you can imagine what happened next. So what happened next is that any researcher on the planet say, oh, okay, now I take any algorithm that exists out there, and I will show you that I can break it with adversarial sample. And then I show you that I can improve it with adversarial training. Of course you can, that's the point. And but that doesn't stop people to write 3,000 papers on try to do that on any possible bonnet on the planet. Okay. So Then we have another bunch of papers that came out more recently on how to use statistical measure to try to mitigate these problems that we just saw. So here was interesting. So the idea is that, for example, adversarial sample, they can break a classifier, sure, they can evade it. But often adversarial sample look very weird. So if you look at the statistical measure of the data, you can tell that probably this sample is being artificially modified, which already tells you that probably it's adversarial, and maybe you don't need to be resistant to it, you can detect it. Similar for concept drift, you can detect statistically when concept drift start to happen to do maybe retraining or something like this. So this idea of using statistical measure to try to detect this problem was used in a couple of papers, and I think this is actually a good direction. Now, I mentioned other 2-3 papers to show you that now we have, this is actually one of mine, so I can't say this is a good paper, but the motivation for this actually is interesting though. So we had so many papers before, but then we start having products. So we start having companies that they sell ML classifiers only based on static features. They say, you know what, I take deep learning classifier, I feed it the raw bytes, and it works, and I sell it, and it's great. And we were pissed about that, saying this cannot work. I mean, we learn in research that anything based on static features cannot work very well. There are packing and obfuscation. So we went on and we implement our classifier, and it did work very well. And then it was like, whoa, why is it working? It shouldn't work. And then you go and you look at it, and we find out very interesting that indeed this can work. And the reason is because packing, the way it's implemented, is not perfect. So if you implement a perfect packer, yes, then machine learning cannot learn anything. But in reality, all the packers that are out there, they're not perfect. So there are parts that are not covered. And what your deep learning algorithm is doing is basically generating by signatures over these invariant paths. So we're using a gigantic thing just to say that, well, there was a little part that was not modified, and my machine learning can actually learn that. More on that later. It seems like we're replacing signature with a gigantic machinery to just learn signatures. Yeah, this is a paper we also published last year, which is very interesting from my point of view, because what we did is we put in comparison machine learning classifier and human experts. We just compared them, and we saw, okay, they're both equally good at classifying malware. So human experts that do that as a work, regular job, they can classify malware with a very good high accuracy. Machine learning classifier can do the same. But what is very interesting here is the fact that if you look at the features that they use, they're completely different. Humans, they classify malware by looking at dynamic behavior. They look at the behavior, what it does, the endpoint it contact to, and they say this is malicious. Machine learning reached the same conclusion using almost only static features. Humans don't use static features, they're difficult to interpret. So we say, okay, that's called normal. But if you force machine learning to use the same dynamic features that are used by human, then it fails. So this, we still don't know why. I mean, there are many possible explanations we came out with. We still need to work on it. But it's possible that we don't do well at encoding this feature. It's possible that there is a lot of semantic in the feature that the machine learning doesn't know. But it's possible that these dynamic features are too sparse. There are something, but the problem is that we both reach the same accuracy by using completely different data. So we try to follow up on this, and we try to actually measure this in practice. And we indeed were able to replicate this. And we were able to show that if you train a classifier only on dynamic features, it works much less than if you use static features. Again, we don't know exactly why. Also because before we reached the conclusion in the other line of research that we should probably base our classifier on dynamic data to be more robust. But in reality, if you only do that, then it doesn't work. So why? Still sort of an open problem. And the last paper I talk about here is actually the first paper was published in ACSAC last year, in which the authors here, Cavallaro and all, they tried to answer the question about, why do we have actually concept drift? Because we know that things change, but what is exactly the change that actually invalidate the model so quickly? So that's still a preliminary result, but it's very interesting. It showed that few malware family can completely ship the classifier results, etc. So I think this will become a much bigger research area in the next couple of years. Okay, so we're done with this. So what did we learn from this? Sounds familiar? That is exactly the same of the previous slide. We learned that, yes, you can evade any classifier. Sure, of course. we learned that we tried them all. Yes, they all were great. Yes. And then eventually, wait 10 years, we realized that, yes, we didn't do the test correctly. So we were sort of cheating. We were sort of selecting the right samples. We were using information from the future, et cetera, et cetera. We learned that adversarial sample break everything. Adversarial training makes everything better if you use machine learning. Well, not so surprising. But we also learned the syscalls that in the previous slide, we say, OK, this is the thing we should probably use because it's more robust. We learned that this doesn't actually work so well. And again, if you use instead things about the bytes and the opcodes and et cetera, tends to work better. And finally, we learned that deep learning classifier, they work still very good, even just by using static features, because packing is not perfect. But basically, what it does is that it learns signatures, and it learns signatures over invariants in the sample. And that brings us to the last area I selected, which is analysis. So analysis is interesting because for many years, actually, that was not a research area because people analyzed malware by hand. So this became a research area actually around the 2005-ish. And here we have the first paper in which academia proposed to use sandboxes. Sandboxes is already something that actually was mentioned even in Cohen's paper, like dates back from the 70s. But as a automated system to analyze and collect data about a malware sample actually became a thing in early 2000. So here we have a few papers. The first one, TT Analyze, became Anubis, the first service online for malware analysis sandbox. The second one from Thorsten Holz, in which they propose in-gas monitoring, how to do instrumentation in order to collect the information. And then we have Panorama. There was this fantastic system, very complicated, QEMU-based, in which they did all system taint tracking to track information inside the malware and whether it was exfiltrating data or not. Starting from here, this thing diverged in many research areas. So, okay, we use sandboxes. Sandboxes became the tool for malware analysis and to collect features. But now we have a lot of problems. We need to stimulate the binary in order to do something because dynamic analysis, of course, only see one sort of execution path. We have all the evasion. We have the problem of repeatability. We have all the design space. How do we design the sandbox? What we use? How do we configure it, etc. So here, just to show you some, but became quite big. So few papers per track here. So on the stimulation part, we have roughly two big classes of solutions. Those ones that they try to use symbolic execution and they failed. I don't know anyone that really succeeded on malware on that. And those ones that they propose to use more system solution to try to force a binary flipping branches to execute multiple paths. That sort of work. I didn't implement it also myself for certain cases. It does work in practice. It's a hell to implement engineering-wise. And it's super heavy, so practically not usable except outside research. But I don't know of any other solution here. In terms of design trade-off, we explore everything which is possible. We try to design sandboxes by using, I don't know, virtual machine, in SMM, in whatever you can put in, your detection or your collection of data. We try to use bare metal. ITER was one of very influential papers because it can show that you can actually use out-of-system collection without using an emulator that is very costly. And then we have a lot of papers that try to explore different trade-offs. For example, we try to look at how long do you need to run it inside the sandbox in order to collect data, and then whether you need to configure the sandbox in one way or the other. Several papers here that explore the design space of sandbox. In terms of evasion, very popular, again, research area. It all started with this paper that is not about sandboxes, but it's the first paper I could find in which they talk about dynamic analysis, counter evasion to try to analyze evasion malware. And then it became a problem of sandboxes. And here we have several papers doing different things. So we have papers that try to detect when there is an evasion. Then there are papers that try to propose new evasion techniques. And then we have papers that try to measure evasion techniques. So we did it all, most right? And we came out with several dozen known detection evasion techniques that can be used depending on which sandbox how you configure your sandbox. But this actually has a practical impact. Today, sandboxes are more resilient to evasion. So eventually, we did learn something about this. Only one paper there on how to make things repeatable. This is a paper from Don and Gavit based on Panda. Fantastic paper. This system, I love it. It solves so many problems in malware. It makes things repeatable. It makes analysis offline. It makes, sharing data. The only problem is that it's QEMU based and it's very heavy. So no one uses it in the industry probably. But that actually is a paper that, will solve a lot of problems that we have today in the malware analysis sort of ecosystem. So I don't know if you know Panda. Panda is a record replay system. So it's a full system based on QEMU that record the entire execution of the system. So only the non-deterministic input, basically. And then it allows you to repeat the execution deterministically. So you can repeat it as many times as you want, and all the program inside the OS will run exactly the same deterministically. So there are other record replay systems. But this was designed for all system emulation. And so basically the idea is that you run the malware inside, you record it, and then later on, you can reanalyze it a year after, and you will still have the same behavior, even though you don't have the endpoints anymore on the internet, etc. So you have perfect repeatability. Plus, you can change the analysis that you want to do when you repeat the behavior. So in 3 years, someone come out with a new analysis, it can rerun the exact same execution and collect data and do the analysis. And you can share these recordings so people can actually have them. So it's actually a very useful tool. It's just that, it's very heavy to do the recording. Not very, very happy, but definitely, QEMU recording, plus sharing the data. It's not huge, but it's several megabytes or more per malware. So if you have millions, that's the problem. So the application for malware was published at Timba, but Panda was published, I think, a year or two before. I don't remember where Panda was. So they published first the sort of emulation technique, and then they publish an application for malware. So the interesting paper is about the one about Panda. So here I cite the one for malware, but the real contribution is in the Panda paper. I get to that I have it in the next slide. So in the last line of research here is about similarity and clustering. So this is also very popular in the malware analysis space. So here we have, similar to what we saw before, try to do clustering based on any possible feature, any possible way of clustering. And my personal experience is that they all fail. Most of the time you try to do malware clustering, you don't get good results. In few selected cases you do. I have a nice picture here from one of my papers. This was a good clustering that you see sub-families appearing. And it only works because this was IoT malware, so there is no obfuscation, no packing. In reality, if you try to use dynamic information for clustering, that you always get messy stuff. You always get clustered and mixed up everything, etc. So we never nail it down, really. But in certain conditions, specific conditions, you can do nice malware clustering within getting good results. And okay, I don't have time to go into it, but this also I think is a very nice area. This is about triage, which is basically the problem of how do you tell whether a sample that you analyze, it's interesting, so it's worth inspecting more, so you want to put humans to see what it is, or is just one of the million of variation that you don't care about? That's a very important problem. And just to motivate the problem, I will not discuss. These are actually all papers published on the topic, these dots. There are maybe 5 papers ever published on this topic. But it's a very important problem. I want to show you just one motivation for one thing we did many years ago. So these are samples from very popular malware campaigns. And this is how many times, how long it took after the sample was collected by a public sandbox for this particular campaign to be discovered. Which means that once they discover, I don't know, Operation Aurora, the sample was already submitted by online sandboxes 4 months before. In some cases, 42 months before. Which means that we did a tremendous job collecting samples, analyzing samples, but we had no idea that this was something interesting to look at. So this is a big problem. And again, there are 5 papers I've ever written on this topic. So I think, that you probably get it is one of my favorite things for me to do in the future. So what do we learn here? So we learn how to design sandboxes, all sorts of sandboxes. So there are pros and cons in which technology you want to use. We learned that, to answer the question, that if you run malware for about 2 minutes, that's all you need. We also test this with machine learning. Machine learning classifiers don't get any better if you feed data over typically 2 minutes period. We learned that multi-path exploration, all the techniques that exist are impractical. There are solutions, but you can't really use it in practice. And then we learned that clustering doesn't really work unless you have very specific conditions. But that's great. It's too slow, and triage is still something that we need and we don't have. So triage is the problem of telling whether a sample you analyze is something that it's hard to define interesting, but let's say it's something that is new. And so you probably want to say that either you discover a new, for example, malware family that didn't exist in the past, or it's just a variation of something that was known. That's why it's sort of a spin-off of clustering, because typically people, what they did is they try to see if it's similar to any cluster they know, and if it's not, maybe it's a completely new stuff. So this is something that, as far as I know, no one actually does. Yeah, it's sort of to detect sort of 0 day. Right? 0 days are to define for malware. What is a 0 day? But a new completely malware strand, let's say, right? And because the vast majority you analyze billion per days, they're just small variation of things that you know. So you don't care about it. Yes, you want to be able to detect them, but you don't care about really looking at it. But those new stuff you want to tell that they're new. And there's not much you can actually do today in order to detect it. Yes, exactly. Things like this, you will be able to tell immediately that this is new. In reality, this thing gets discovered because some company gets called and say, oh, my computer crashes, and this is a big customer. They go there and they check and say, whoa, what is this stuff? They analyze manually and they say, oh, yeah, that's a big targeted attack. Yeah, that big targeted attack was collected 5 years before, but no one actually knew it was a big targeted attack. Okay, so this is all I got. I need to wrap up very quickly. So this is my selection of the main question we try to answer. There are many more that I couldn't fit, but I think we covered the main areas that people try to investigate. And now I want to give you my selection of something that I think is, we should try to answer in the next few years. Okay, very biased, of course, but that's the point of, I guess, the keynote. So number one is triage. I already told you. I mean, that was clear. I really think that we need more work in this space. I really know only 5 papers ever published on this topic. And it's an important problem, very important. I think industry should probably have something for this. So we need to do it. In particular, I think there is no machine learning paper ever written for triage. As soon as machine learning people figure out, we will have 3,000. But maybe here it actually is something that we could have. Second, again, on machine learning is, again, why do machine learning classifier don't work well when you do on dynamic features and human only use dynamic features? So this is something we need to figure out. We're doing something wrong. It's either a technical problem, feature encoding not done properly, or it's a more important problem, maybe about the fact that humans use information that are not in the data, that are just in their sort of general knowledge, and the machine learning doesn't know about it, or I don't know, but that's something we should be able to answer this question. Number 3 is about analysis. I didn't talk about this, but all our analysis studies are to analyze window malwares, maybe kernel rookies or something like this. But we have malware for firmware implants. So things like, the NSA problem of, hey, they infect the hard disk firmware, and then it's game over. And there are almost no paper on top of that. I mean, no one knows how to analyze them. No one knows even how to collect them or extract them, even though there is a piece of malware that needs to install them. So technically, it should be possible to extract this. But there is no study on it. And we tend to forget about it because it's a very difficult problem. It's like, I don't know what to do about it. I'm talking about example. I don't know if you remember the NSA leaks in which they show that what they did is they had, they call it inflights. So basically, you have a malware that exploits something or update, depending if it's a vulnerability or just an update of the firmware of the hard disk. And then for many manufacturers, they install a malicious firmware in the disk. At that point, it's game over because the malicious firmware can always pollute the operating system at runtime. You can never get rid of it. You can never detect it because if you ask to download the firmware, it will give you the clean one. So at that point, you don't know if it's installed into your organization and you lose control of everything there. So this thing exists. It's been used in the wild, very rarely because it's very difficult to do. But the industry doesn't really have any way to sort of detect it, analyze it, know what is going on. I don't know. Next is, yeah, this bugs me. So we have now these three things. We have some sort of behavioral models. We have machine learning classifier. We have still signatures based on bytes. How do they all sort of interplay with each other? How do we can combine them in an efficient way? Is the machine learning replacing the signature? Are they doing the same job? Are they detecting different stuff? We didn't really study this so far. What is the right way to put everything together and to finally, collect all these branches of research and try to get, something that give better results. This one for me is the elephant in the room for the analysis part. So when you use a sandbox, you need to contain on the network level the malware not to do nasty stuff. Ask any people how they do that, and they say we do our best. And that's the best you can get. So there is no clear guideline on what you should do except do your best. And any company will say we will do your best. Because clearly they cannot cut the internet connection, otherwise malware will not work. But we all know that people submit to sandboxes malicious stuff on purpose, used as a trampoline to launch attacks. So I don't know, academia, there are maybe two papers or three on the topic. It's a difficult problem, but we probably should study it a bit more. That's also a general question I have. So we study, I didn't discuss this much today, but we study everything for MS-DOS, for Windows, then for Android, then for Linux, then for macOS. Every time we reinvent everything. But how does this OS or the ecosystem of the application influence and change the behavior and then the evolution of malware? And more importantly, the second question is that once we learn something, for example, for Android, some more results I showed you before, they were tested only on Android malware. Does this result then generalize in general to malware, or is something that only is true for Android? We don't quite know. I mean, we cite it as general thing, like, oh, they test adversarial thing, they test on Android. Is that exactly the same on other domains? We don't quite know. Oh, you were expecting that, of course. LLMs. This will probably be the first question to be solved. There are already a lot of papers now coming out, but it's still, I don't know where it's gonna fit in my metro map, right? So is it gonna be something to explain report? Is it gonna be something to generate variants? Is it gonna be something that does a bit of everything? I don't know. Figure out where LLM can play a role here in the picture. I think it's important. Probably will come out very soon. Concept drift is another thing that is very important. In particular, now we got the first paper last year on how to explain it, but there are still things that we don't know. For example, does a concept drift affect all type of feature at the same way? Probably not, right? So you will expect maybe static feature to be more affected. Maybe if you have something that is behavioral based, is less affected by concept drift. That depends on the type of concept drift, though. If it's a new family completely, maybe also affect dynamic. But how different set of features and classifier, they more resistant to concept drift, it would be interesting to know, right? Maybe we know that, maybe we can learn that certain things work a bit less well, but they're much more resistant to concept drift. You can actually deploy them and use them for longer time in the wild, for example. And the last one is sort of, I want to have something more theoretical. I suck at theory. But this is, for me, the most theoretical I can came out with, which is, what does it even mean for something to be hard to evade? There are so many papers that they say it's very easy to evade these signatures. So I propose this other model, and this one is harder to evade. What the hell does it mean to be harder to evade? Sure, I mean, some model is very easy. You change a couple of bytes and you evade them. Some of them, no, you need to do a better transformation. But these better transformations are automated. So is it really more complicated? I mean, the bad guy just press a button and he create a variant. If he needs to add 1 byte or if he needs to insert, code here and there, is it harder? So is there a way to actually formalize this and have a measure of what does it really mean having different classes of complexity, that this is more difficult than this, or it's just different for humans seems more difficult because it affects more bytes. I don't know. This, I don't know. I think we should probably have an answer for this, because otherwise every paper claims that mine is harder to evade. And I don't know what it means to be hard to evade. Matrix? What is a matrix? Now, how to evaluate the difficulty of evading something? Yes. Yeah, for a metric. Could be, or it could be just a couple of classes of this is harder than that, and doing this costs more than that, and you need to pay something more, which is maybe not time, because generation time is sort of free. Could be like, I don't know, you lose flexibility in your malware, you make it more weird, and then it's easier to detect by statistical patterns. But we need to have something that says that this is worse than that when you try to evade it. And this is my last one, which is static and dynamic feature, both for models, for machine learning, for everything that we did. They've been there since the beginning. And there have always been hybrid systems that use both. But we don't quite know yet what is the best way to use both. So when we try to design classifier, for example, we see that if you use both, you get a bit better result at the same time. But maybe it's costly to use both because dynamic feature costs time to collect. So maybe you want to use static first and dynamic only in certain cases. Can you use static and predict whether you will need dynamic? I don't know. The right way to compose them to get something that is more efficient, I don't think there is much study on this here. Yeah. Dynamic alone is worse than static. Dynamic plus static is better than static, but marginally. So it seems like you improve the classifier by, don't remember the result, by few percent, don't much. But the cost of doing that is much bigger. So the right way to do it is probably not to do hybrid, but to do static only and know when you need to add dynamic. Or do static only and use dynamic only for certain classes. Or I don't know. Okay, I'm done, so I answer your question when I leave this one here. So we have several possible ideas. So one thing that we notice is that dynamic is very sparse. So it means that a lot of samples, they don't show dynamic behavior, even though they should be there, because they didn't work, the endpoint is down, etc. So machine learning tend not to pick up this as very reliable because, well, most of the time it's missing. So that could be one of the possible reasons. Humans seems they don't care. Humans look at it and they identify that this is weird and it's probably enough. Machines probably give lower weights to these things that are very sparse. That's a possibility. The other thing that we imagine is the fact that our feature encoding for dynamic feature, for static feature is very easy. You know, you just encode is just a number, it's just a number of sections, it's just whatever. But for dynamic, how do we encode a URL? Right, so a lot of people do this one auto encoding is just basically a unique thing, and you say one if it's there or if it's not there. That's very bad. So you don't think that way. So probably we need a better way to encode features that could actually capture more information for the machine. I mean, I'm saying that probably there are many problems and they all contribute. I don't know which one contributes most, and I don't know if one of these problems, if you solve it, then all in a sudden improves the results. But I don't know. That's why it's, for me, still an open problem to know exactly the. I wasn't very good.
So we organically started the Q&A session, so that's fine. So, but we're running a little bit out of time. I would maybe ask for a final question if anyone has one. Okay,
yep.
Go ahead.
Thank you.
One question I have is that we used to worry when we were doing dynamic analysis that if the malware just computes pi for 3.5 minutes, it will defeat our dynamic analysis technique, right? So why doesn't that happen, or does that happen, and how frequently does that happen?
So this is something we try to measure. Indeed, this is the easier way to evade a dynamic analysis system. Just wait long enough. There are different ways to do that. So one is to simply wait, sleep, for example. And a good number of sandboxes, they try to cope with that. They skip sleeps. They do fast forward on time to try to evade this kind of thing. Not all of them. We tested some sandboxes. Some do, some don't. But we measured this on a very large number of samples. I don't remember, 100,000 or something like this. And frankly, not so many malware do that. I don't remember the number in my head, but it's on that paper I cited before. It's maybe 3-4% or something like this. So not many actually malware wait before they do their malicious stuff. And that's why on the grand scheme, if you don't cope with this and you only skip sleep, that is the easy one, you probably miss just 1 or 2% of the data by analyzing 2 minutes. And at that point, the gain is if I go at 10 minutes, I can get this 1 or 2% more, but going to 10 minutes costs me a lot, right? So probably it's not worth doing that. And we even noticed that strangely, machine learning classifier, they plateau at 2 minutes. And then some even degrade a bit if you feed more data. Probably because at this point, the data is more like this, all the same stuff that it's doing. And you sort of dilute the interesting part. That's, I don't know, we didn't investigate that much. But it seems like the peak is really before 2 minutes. We also measure how the code executed by the malware, so the coverage of the code, changes over time. And there again, you see that typically you reach maximum coverage after 30 seconds. And after that, you keep executing new system calls, but they come from the same piece of code. So it's the same routine that generates more system calls. So if your goal is to get more endpoints, for example, for network, probably you want to run at 20 minutes because you discover more values. But the behavior is the same, remain the same after typically 20, 30 seconds.
Thank you. We got great clustering results.
Yeah, please. Yeah, please.